Okay, so last time, we presented this idea of, if you have, say, simplicial complexes K1, K0, K2, and then all the way up to Kn, and perhaps you have simplicial maps, F0, F1, F2, and here Fn minus 1, then one can take homology of each simplicial complex, right? So you get Hn K0 initially with coefficients in Z, Hn K1 Z, Hn K2 Z, and all the way up to Hn Kn Z. And we also saw that these simplicial maps, F0, F1, F2, and so on, induce these star operators here. Right? And we saw sort of several ideas. So for example, if in here we pick some bases, so say that you have these crosses like this, and here you have these crosses as well in here, and perhaps you have 3 basis elements in here, and then some stuff in here as well. Then sometimes it is possible to pair sort of basis elements with basis elements via the F star maps. So for example, it could happen that this basis element goes to this basis element, and then this basis element goes to that basis element, and perhaps this basis element also goes to this basis element, and maybe these do the following, right? And perhaps, this goes to that, this goes to that, and this goes to that, and so on. So the first sort of observation was that sometimes sort of can pick bases in each Hn Kj Z such that a basis element, so F star maps a basis element to a basis element. Right, so for example here, another observation is that we have sort of these, for example, 2 basis elements that are mapping to the same basis element. So we introduced this idea of the Eldar Rule. Which in sort of a few words says that one keeps the older class. And one way in which we can sort of interpret this is that, again, sometimes we can pick not only bases, but compatible bases. And the word here is compatible in the following sense, that, again, if these are the homologies of the different spaces, and these are the star maps, then perhaps it is possible to choose different bases. So now diamonds instead of crosses. So I have 4 of these guys in here. Then I have 3 of these guys in here. In such a way that a basis element now goes to a basis element. And now, instead of this basis element also going to this basis element, we've picked a different basis so that this goes to 0. Right? And similarly, with this guy, sort of this basis element goes to this basis element goes to that basis element, and now this guy, instead of also going to that one, now goes to 0. So that is the idea of sort of picking compatible bases, in the sense that a basis element either goes to another basis element or to 0, and there are no collapses as one moves to the right. But as we saw with one of the examples, this is not always possible. If we're computing things over the integers, and the problem was multiples. This idea that perhaps a basis element can go to some multiple of another basis element. So one would like to get rid of this by perhaps dividing by n, but that is not possible unless we are in a field. So the idea is replace z by a field f, perhaps like the rationals, the reals, maybe the complex numbers, or even the integers modulo a prime p. Correct? So now that we're here, then the question is, okay, now how do we think about homology, but now doing the operations over a field? So that was the last thing we introduced last time. So what's this idea of doing the computations over a field? So just to remind ourselves, we started with this idea of chains over a field F, which is denoted Cn Fk. And these are just the things that we're going to call n chains over the field F. And these are functions from n simplices of k to f. In other words, if you pick an element in Cn k z, f, then one can write it as lambda 1, sigma 1, lambda n, sigma n, where lambda 1 through lambda n are elements of the field coefficients, and sigma 1 through sigma n are n simplices. Okay? Another way to think about this is as vectors. So if you take the coefficients and you put them in a vector lambda 1, lambda 2, lambda n, then this is an element of f to the n. Right? So just as before, we can think of elements in here as functions from n simplices in here to f. We can write them as these types of linear combinations, or we can think of them as vectors with coefficients in f. So right away, there are a couple of things that come out of this picture. The first one, so let me put a remark in here. So the first remark is that, okay, so if this guy looks like vectors, then it is in fact, it's a vector space. Over F. The second observation is that the n simplices of K form a basis for C and KF. Okay? And then, given this fact, we get that the dimension of Cn Kf, again as a vector space, is equal to the number of n simplices of K. Right, so all the linear algebra that we know can be used now to understand these n chains here. So if we have chains, then hopefully it is not that difficult to see that we also have boundaries. So we also have boundary maps. Right? And this time, or just as before, they're going to go from n chains with coefficients in F to n minus 1 chains with coefficients in F. And similarly, it's taking an n chain that perhaps looks like this to the n minus 1 chain that you get by just applying the boundary map as before. Okay? And then the remark is that now delta n is a linear transformation. Right? So a linear transformation in the linear algebra sense. It goes from this vector space to this vector space, and it acts linearly. So in particular, one can look at it as a matrix. So you can think of delta n as a matrix with entries in F. Okay? So what do we have thus far? We have the n chains now with coefficients in the field F, which again are linear combinations where the coefficients are in F. We also have the boundary maps, but now the boundary maps look like linear transformations, so we can think of them as just matrices. And several of the, or at least most of the things that we've seen before continue to hold in this case. So we still have that if you take two sequential boundaries, you get 0, because this was true for n simplices. So in particular, it is true for a basis. This implies that the boundaries over F, which are the image of delta n plus 1, is a linear subspace subspace of Zn kf, which is the kernel of delta n. And we can still think about the homology of kf with defined as the cycles modulo the boundaries. Okay, so this is what we call homology with coefficients in the field F. With coefficients in F. Okay, so let me do a couple of examples just to see how this works in practice. In particular, I want to explore what the choice of F has to do with the final result of this computation. Okay, so for this example, I'm going to take K to be the following simplicial complex. So it's got U0, U1, U2, U3. And it's got tau 0, tau 1, tau 2, tau 3, and tau 4 as edges. And it's got sigma here as this two-dimensional face. We orient the simplices in the usual way, like that. And then I'm going to let my field F to be the integers mod 2. Okay. So usually when we write the integers mod, let's say n, we write classes like this. In this case, I have two different classes. I'm gonna simplify the notation, and I'm just gonna use the numbers like this. And I'm going to make precise what the operations are. So, for example, if I want to look at the addition table in Zima 2, then I have to say how to add things. So 0 plus 0 is 0, 1, 1, and 0. So 1 plus 1 is 0. In other words, 1 is minus 1. Okay? And if you're thinking about the multiplication table, so 0, 1, 0, 1, then you have zeros everywhere except here at the corner. Okay, so these are the operations of this field. And again, we know that it's a field because every non-zero element has another element that when you multiply by it, you get 1. So what I would like to do now is I would like to compute the first homology of this complex. So here's the goal. The goal, compute H1 of K now with coefficients in Z mod 2. And as always, what we're going to do is we're going to maintain two matrices. We're going to maintain delta 2, and we're going to maintain delta 1, right? Because we care about the kernel of this guy, meaning the cycles, and we care about the image of this guy, meaning the boundaries. Okay, so I'm going to use the bases given by the simplices. So here is sigma And I have tau 0, tau 1, tau 2, and tau 3. And here in delta 1, I have tau 0, tau 1, tau 2, 3, and 4. And then here I have U0, U1, U2, and U3. And let's just fill up the matrix. So if you look at sigma, right, so the boundary of sigma should be tau 0 plus tau 1 minus tau 4, right? So tau 0, tau 1, and I guess I missed 1, so 4 in here, and then minus tau 4. But remember that in Zima 2, minus 1 is equal to 1. So I'm going to remove just this guy here. Okay? So that makes the boundary matrix much simpler. It's just telling me what are the one simplices which are boundary of these two simplex. And the same here. So tau 0 would have boundary 1 minus 0, but then minus 1 is equal to 1. Here we have 1, 1. Here we have 1, 1. And then 1 here, and 1 here, and 1 here. So that should be the two matrices of the boundary transformations with entries in this field, Zima 2. So what I'm going to do now is I'm going to reduce, we're going to do the same thing that we did before over Z. I'm going to reduce this matrix, okay, using row and column operations. And then I'm going to record what are the row and column operations I'm doing. And every time I do a column operation in here, I'm going to keep track of what is the corresponding row operations to do here so that I can change the basis accordingly. Okay? So let's see. So in order to reduce this matrix, and by the way, I'm going to use Python indexing. So we have 0 row, first row, second row, third row. So here are the operations that I'm going to do. So I'm going to do in here row 1 in the delta 2 side. I'm going to do, sorry, in the delta 1 side, I'm going to do row 1. I'm going to assign it row 1 plus row 0, right? So that clears that 1 in the second row. And then I'm going to also erase the columns in the first row. So column 3, I'm going to assign it column 3 plus column 0. Row 1 is going to be row 1 plus row 0. Okay? Now, column 3 is going to be column 3 plus column 0, and then column 4 is going to be column 4 plus column 0. Okay? So the matrix that I obtain is now going to look like this. So I'm going to have a 1 in here, and then I'm going to have 1, 1, 1, 1. I have 1 here, 1, and 1, and 1. So I used this to remove this entry, and then I used these two operations to remove this entry and that entry. And let's see what the effect of the operations was. So remember that when you're doing row operations, what you do is you affect the bases that you are adding by. So here you would have, say, U0 minus U1. And there are no other row operations. So this is no U2, U3, and U4. And now remember that minus 1 is the same as 1. So, boop. And now the column operations. The column operations are easier because they are exactly what they affect the basis in exactly the same way that is described here. So this is tau 0, tau 1, tau 2, and then tau 3 would be tau 0 plus tau 3, and then here would be tau 0 plus tau 4. So that's the basis change. And in the delta 2 side, what I do is I turn column operations into row operations. So, and they, remember that they switch places. So now row 0 gets affected via row 0 plus row 3. And I put a plus in here. I should have put a minus, right? So that would have been the inverse thing, but again, plus is equal to minus over zima 2. And then the row 0 gets affected via row 0 plus row 4. And then the matrix that results from those changes, again, is going to have the same basis I have here. So T tau 0, tau 1, tau 2, tau 0 plus tau 3, and then tau 0 plus tau 4, and then tau 0, right, so I'm adding, so to row 0, I'm adding row 0 plus row 3, so that doesn't do anything. And then to row 0, I'm adding row 0 plus row 4, so that adds a 1 in here, so this gets removed, 1 and 1. Okay, so those are the matrices, and we continue with the operations, right? So now let me use this guy to remove that, and then the columns. I guess the comment to make right here is hopefully you can see that the operations, the algebra of reducing the matrices is much easier over zima 2 because of things like 1 plus 1 equals 0 or minus 1 equals 1. So it just simplifies a lot the algebra, and that's why implementing the reduction algorithm over zima 2 is not super, but much easier in the computer than with the integers, for example. So let's continue on. So 2 and 1, and now the reductions I'm going to do are, so I'm going to use row 2, 0, 1, 2, yeah. There is a 0, 1, 2, 3. Yeah, let me change that. So 0, 1, 2, 3. Okay. Yeah, so now let me use row 1 to change row 2. So I'm going to let row 2 be row 2 plus row 1. And once I do that, right, let me now clear the columns, right? So I'm going to make column 3, so 0, 1, 2, 3. I'm going to make it column 3 plus column 1, right? And then column 4 is column 4 plus column 1. Correct? So now the matrix that I get, so I still have a 1 in here. Then I have a 1 here, but I've removed everything that is to the right. Here I went down, so no longer do I have this guy, but I do have this, and then the 1 that I had here canceled that guy out, and then Here I have a 1 and a 1, and that's all I have. So here in this side, I have tau 0, tau 1, tau 2, and then the way the columns changed is that I added 1 to 3. So now I have 0, 1, and 3, tau 0 plus tau 1 plus tau 3 as the basis element, and in the last column I have tau 0 plus tau 1 plus tau 4. Okay, and now the rows. So I used row 1 to affect row 2, so I get now U0 plus U1, and here I have U1 plus U2, and then here I have U2 and U3. Right, so those are the basis elements I get, and as before, we turn these column operations into row operations here. So row 1 is now row 1 plus row 3, and then row 1 is row 1 plus row 4, and then the matrix that you get is sigma in here, and then the basis elements are going to be tau 0, tau 1, tau 2, tau 0, so the same as there. So tau 0 plus tau 1 plus tau 3, and tau 0 plus tau 1 plus tau 4, and then the only thing that survives is the last entry. Okay? So we're almost done. So the only thing that is left is to add row 2 to row 3, and then add column 2 to column 3. And let me do it over here so that I don't lose the complex. So 2, 1, the goal, when I erase it, we know what it is. So let me erase the basis here. The basis will probably change, so we're gonna also remove this. And let's just think of the operations. So we're gonna do, what's that? We're gonna do row 2 plus row 3. So row 3, we're gonna assign it row 2 plus row 3. And once we've done that, we're going to assign to column 3, column 2 plus column 3. Okay? So once you do that, the basis that you're going to obtain, I mean, the matrix that you get, first of all, is just simple like that, because the square at the bottom is removed. And then here you get the following basis elements. You get tau 0, tau 1, and tau 2. Then you get tau 0 plus tau 1 plus tau 2 plus tau 3. And then the last one is going to be tau 0 plus tau 1 plus tau 4. And then across the rows, you're going to have U0 plus U1, U1 plus U2, and then here probably U2 plus U3. And U3 and U4, U3, and yeah, that's it. Okay? And then here, for the other one, you're just going to have tau 0, tau 1, tau 2, in the same columns. So tau 0 plus tau 1 plus tau 2 plus tau 3, and then tau 0 plus tau 1 plus tau 4, and then the last entry is like that. Because, right, we took these column operations and turned them into row operations like so. Okay, so right away, we can identify a basis for the kernel. So zeta 0 and zeta 1. And then zeta 1, which appears here, is a basis. It gives you a basis for the image. So this is zeta 1. Okay, so I guess it doesn't hurt to look at what these guys are here in the complex. Okay, so if this is zeta 0, well, then notice that this is exactly tau 0, tau 1, tau 2, and then minus tau 3, which is the same as tau 3. So that is the cycle along the complex that is capturing this whole. And then zeta 1 is tau 0, tau 1, and tau 4, which is exactly the boundary. So we've succeeded in that regard. So over here, what we conclude is that zeta 1, which is the kernel, right? So this is the kernel of delta 1, is generated, right? So it's generated, so has not only generated, but has zeta 0 and zeta 1 as bases. And that means sort of over Z2, right? In other words, every element in here can be written as a linear combination of these two using coefficients in Z mod 2, which is again 0 and 1. Okay, so these are the only coefficients you have to write down linear combinations between these two. In other words, this is actually equal to 0, the two elements, and then their sum, which is, what is their sum? Tau 2 plus tau 3 plus tau 4. Right. Okay, so those are the cycles. And similarly, B1 which is the image of delta 2, has as bases zeta 1. So this is just 0 and zeta 1, like that. Okay? So now when you take homology, again, remember that this is the cycles modulo the boundaries. Then you're back to looking at this table. You're asking, okay, which of these cycles are not homologous to the boundaries, right? So 1 is certainly a boundary, and then this element is homologous to this because it differs by a boundary, in particular zeta 1. So this is exactly 0, and then the class of zeta 0, right? And then here, notice that zeta 0 plus zeta 0 is 0. Okay? So this really is the same thing as Z mod 2, right? Where we're pairing sort of 0 with 0 and the class of zeta 0 with 1. Okay? So the goal of going through this calculation was to just illustrate how the algebra changes depending on what you put in here. So in particular, when we were doing the matrix reduction, the reduction algorithm, all the operations were happening here, okay? So the simpler your field is, then the easier these operations are going to be, okay? Okay, so let me give you a couple of remarks. So, in general, when we compute homology, so in general, let's put it here. So in general, the homology of a space with coefficients over a field, this is going to be a vector space. Again, over F. So in the previous example, we got a vector space of dimension 1, just sigma 2. So in here, what we're going to get is that this is going to be as vector spaces. So some product of D times F. And then the idea is that this has dimension equal to D. Okay, so that's the number of times this F is being repeated. In the previous example, we got a vector space of dimension 1 again. The second observation is that if you calculate the zeroth homology of a complex with coefficients in a field, then again, this is going to be some vector space. But it turns out that we know what the dimension is going to be. This dimension is going to be Betty 0 of K. In other words, it's going to be the number of path-connected components. Components of K. Right, so regardless of what the field is, you're always going to get the same dimension. And that dimension is going to be Betty 0 of the complex, which again is the number of path-connected components. Before, when we put a Z in here, we got a product of Z's, and we have beta 0 of those. Okay, so that's the parallel between the two stories we've seen thus far. Now, let me give you a less trivial example just to illustrate what happens when we change the field F. Okay? So, for this example, I'm going to use the projective plane. So we're going to compute the homology of RP2 over several fields. So remember that one way to think about RP2 is as a disk where you take boundary points that are antipodally opposed and you identify them. So this side is the same as that side. Okay? And then one way to triangulate RP2 is by taking a hexagon putting a small triangle in the middle and then dividing it like so. Right? So in these, so we're going to call this K, right? And then in this complex, I have that this is U0, U1, U2, and then U0 again, because these are diametrically opposed, and then U1, and then U2. Let me call these U3, U4, and U5. I'm not going to name the edges because it gets too messy, but let me call the two faces. So sigma 0, sigma 1, sigma 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so I have 10 two-dimensional simplices and 6 zero-dimensional simplices. Okay, and let's just compute the homology of these space. We already did the integer version at least. We computed that this was z, right? Because it's path connected, so only one connected component. H1 of k, we computed it as z mod 2, right? And the generator, or I guess the way to think about the generator was that if you took zeta to be 0, 1 plus 1, 2 minus 0, 2, then this guy is in fact just the class of 0 and the class of zeta. And we also computed that H2, or maybe we didn't compute it, but the claim is that if you compute this, then you get 0. There are no, and the reason is that there are no two-dimensional cycles because the space, at least over the integers, because the space is not orientable. Now, what I would like to do is I'd like to compute the homology of RP2, but now over Z mod 2. So now let's compute when I take coefficients in Z mod 2. Okay? So from the remark that we have before, we have that H0 of RP2 is still just Z mod 2, right? So it's going to be a vector space, and its dimension, meaning the number of times the field is repeated, is going to be just the number of path-connected components. So that's that. In H1, one can still, one can compute this using perhaps the matrix reduction like we just did before, and one would see that this is also Z mod 2. The interesting case comes in the next homology group, in the next homology vector space now. So if you let phi be the sum of all the two simplices, right? So take the sum of all the two simplices. So this is now an element in the two chains of K with coefficients in Z mod 2. So notice that if you take the boundary of phi, then each edge is going to appear 2 times. And since 2 is 0 modulo 2, then this is actually a cycle, okay? So in particular, phi is in Z to 2 like that. And since there are no 3 simplices, then in particular one can see that, or in particular one can show that this is the only class that gives you homology. In other words, H2 of K with coefficients in Z mod 2 is actually the class of 0 and the class of phi, which is, again, Z mod 2. Okay, so I want to illustrate with this example that before we had something that was Z with coefficients in Z. We had that it was Z, Z mod 2, and then 0. But if you change to Z mod 2 coefficients, then you get Z mod 2, Z mod 2, and Z mod 2. Okay? So we already are seeing a difference in the homology. That it's saying that the algebra, that changing the algebra changes the answer because the space is complicated. Let me do one last example And I'm going to do it now with Z mod 3 coefficients. So same complex, but now we're going to do Z mod 3. So in Z mod 3 again, we get still that H0 of projective plane is still Z3. Let's think about H1 now. So for H1, one can show that there is some psi in C2, so a 2-chain, and I'm going to put it with Z coefficients just to illustrate the point that I'm trying to make. There's an integer 2-chain, so that if you compute its boundary, you get 2 times phi, 2 times psi, which was the generator we picked for the homology before. So just to keep you in the loop, this was U0, U1 plus U1, U2 minus U0, U2. So one can show that there is an integer 2-chain, so that if one computes the boundary of it, one gets twice the generator of the homology in degree 1. One can actually psi is going to be also a sum of the simplices with plus or minus signs appropriately chosen. So what happens modulo 3 is that 2 is equal to minus 1. So that implies that psi is a boundary, and therefore it kills the homology in degree 1. So in particular, H1 of K with Z3 coefficients is now 0, because this was the only class that we had before. And similarly, one can show that that H2 of K with coefficients in Z mod 3 is also 0. So again, this is by showing that there are no cycles. There are no 2 cycles. So in summary, if one wants to compute the homology of RP2 with coefficients somewhere, and then perhaps the coefficients we want to take are maybe Z or Z mod 2 or Z mod 3, right? To say that you want to do that computation, and we already did. And we want to do it in degrees, let's say 0, 1, and 2. Then the answers that we get are as follows. In dimension 0, we're always going to get 1 copy of the coefficients because the space is connected, it's path connected. But now in dimension 1, we saw that we got Z2 here. In Z2, we get Z2. In Z3, we get 0. And then in dimension 2, with these guys, we get 0. With these guys, we get Z2. And here we get 0. So these 3 columns are completely different from each other. And what he's saying is that RP2 is complicated enough that by changing the algebra, meaning by changing the place where we're doing our operations, changes the answer sometimes drastically, okay? So what we're gonna see next time is that doing the reduction over fields is much better algorithmically, but then it doesn't give you the full answer because there are many spaces that have sort of the same picture over one of the of the fields. What is going to be the case is that by changing fields, we're going to be able to pick up sort of intricacies of the space. Okay? So let's stop there. And